In this video, I want to talk about vacuum processing. This is a concept that's super important for how database management systems like Postgres actually make sure that databases can be used for long periods of time without running into storage issues. To recap, in the last video, we talked about multi-version concurrency control, and at the very end of the video, I touched on a problem that tends to be created because of MVCC. To recap what happens, if you remember how we modify a database, every time we actually create or insert a tuple and we insert some information within our database, what's happening is that we create a version of that tuple. So you can imagine we have like a V1 here and we insert some new row into a table in our database. With that new row, it has information X. For example, that could mean we have some employees table and the row within that table has everything that we need in it, like a name, an employee ID, maybe their salary. But then something changes about that employee's information. Maybe we update that row to have some new information. So what actually happens under MVCC is that we create a new version of that tuple, and now it has information Y. Let's say the name stays the same, the EID stays the same, but this person got a raise, and now their salary is twice as much. So now what would actually happen is that this original version, V1, would say, hey, this is an old tuple, and now we should point to V2. So what this means is anyone who's querying our database to try to get the information about this employee should actually be querying for V2. And that way, this V1 tuple right here is actually not that useful anymore. So what we pointed out in the last video is that this tuple right here, this V1 tuple, is something we call a dead tuple. And I want to expand on this term right here, actually, tuple. I would say the easiest way to understand this and think about it for the sake of this video is just a row in a table. So you could imagine that this actually right here is a tuple. It is something that we are inserting into the database. But in reality, what tuples actually have is all the information that we're inserting into our table, but a couple of extra pieces of information. So that extra information is actually super important for how some of these processes like vacuum work. So the key parts of that extra information that you should know about for the sake of this video are the txid that created it, the txid that supersedes it, and just the actual information. So that would mean like the name, EID, the salary in this case, but I want to expand on each of these things and I'll break that down. So by txid, if you remember from the last video, we discussed transactions. So transactions, again, are just a way to interact with the database. They're simply a sequence of operations that we do on the database. And this should probably look familiar, but the way in which we initiate a transaction is with this begin command, and then we have some sequence of operations, and then we commit. So behind the scenes, what's happening with the database internals in this sense, where we actually have a txid that keeps track of these transactions. So the txid you can think of as just sort of some unique identifier for each of these different transactions. So when we're talking about dead tuples and we're talking about tuples in general, we have some information in there that tells us, hey, this is the transaction that actually created this initial tuple. So to really hit things home, for this V1 tuple that we created here, there's some extra information that says, hey, transaction 1, 2, 3, 4, 5 created this V1 tuple. And then the txid that supersedes it could actually mean anything like an update or a deletion. Essentially, what is this arrow pointing to? Is there a new version of the tuple that we need to care about? Is this the latest tuple that's in our system? So maybe in this case, transaction 1, 2, 3, 4, 6 created V2. And that information could tell us, hey, this is where tuple V1 points to. So I know a lot of this is kind of confusing, but hopefully as this terminology becomes more comfortable, then it'll make a lot more sense. Great. So now let's think about how vacuum should actually function in order to save our database from a bunch of these dead tuples. So to help us understand, I have pictures of blocks stacked on top of each other. And to really hit home how vacuum should actually work and how it should make sense visually, I want to point out that this block right here could represent a just database state that we have, where we have a bunch of pieces of information. Some of these are probably dead, some of these are, in a sense, like live tuples, some are dead, like I said, and we need to figure out what can be removed. But this is the after state. So this is what our database, or this, in this case, this table can look like after the vacuum actually goes through and cleans things up. So let's say in this case that this first block right here, this yellow block, is dead. This points to something that is an actually new tuple that we care about, and we want this data to persist in our database. But this yellow block right now is useless. Then we can also say that these two blocks down here are the same thing. These are also useless, and they point to some V2. So that means, in this case, all of these can be removed. So in this case, the vacuum goes through, and it essentially just removes those parts of the database. It removes those tuples. So this is an essential function of the vacuum, cleaning up dead tuples. But to really understand some of the specifics, there's two types of really vacuums that happen in Postgres. The first is the concurrent vacuum. And this, in most traditional senses, is just referred to as vacuum. So this is what really goes through and does like a very simple job of removing dead tuples, and does a couple other things that we'll talk about in just a second, but it'll mark this space here available for reuse. Essentially, these extra spaces now are free for new tuples to be inserted, updated, basically new versions to exist. So for this process to actually work, a share update exclusive lock is acquired. Now, understanding the specifics of what a share update exclusive lock actually does isn't necessarily important for this exact example, but essentially what this means is that anyone else can still sort of read when this is going on. So if the vacuum process is going up and it's cleaning these sort of dead tuples here, and we can apply this to our example of the employee database from earlier, let's say we have a client that wants to read how much money is in their salary amount. They want to check essentially the employee salary for someone who's in that company. This is still possible when concurrent vacuum is going on. And this is why the name sort of has this inherent concurrent to it. So concurrent operations can still happen while this is going on. A write can't happen, obviously, because we are changing things about the database state, but you can definitely read while we're cleaning up these dead tuples, because like we explained, these dead tuples actually shouldn't affect current database operations. These are just sort of useless pieces of information that can be removed. Another key distinction about the concurrent vacuum is that space is not returned, which means, specifically, this means in terms of returning space to the OS. So your actual operating system, whatever is sort of storing our database, will not get back extra space from clearing out these dead tuples. It's simply getting marked for reuse here. But this is still a very, very important process, and the concurrent vacuum can run super often, should be run super often when you're sort of trying to manage your database state. The second actual type of vacuum that a lot of Postgres developers will be familiar with is the full vacuum. Now, the full vacuum still essentially will do the same purpose, will serve the same purpose, but there's a couple of slight differences. So like we were talking about earlier, in this case, the space actually is returned to the OS, which means that we are actually rewriting the table again to a new disk file. So what that means is in this example, if we have this sort of group of blocks and we identify these dead tuples here, what we do is we instead will write this new table here from scratch, and we will just have the actual blocks again that we need. And this extra space that was here before can actually be returned to the OS, and we can reuse that again freely however the OS decides to allocate that memory. And because we do that, because this is a bit more of an intensive process, full vacuum actually requires an exclusive lock. So that means reading and writing can't occur when full vacuum is going on. So what that means in terms of actual development is people might run full vacuum less often, but it's still a potentially super helpful thing to do if you're trying to return space to the actual operating system. Now, I want to talk about something that's a super important part of vacuum that's sort of a secondary task that it does. So this is related to txid wraparound. So if you remember earlier, we were explaining what a txid actually is. So just to recap, it's sort of an ID for a transaction. And a transaction, again, is a sequence of operations that we do on our database. And so that's any client interacting with our database, getting information, updating things, altering tables, anything like that is a transaction. And this is just sort of a way to denote what that transaction actually looks like. So the way transaction IDs work internally is that they're numbered. And the numbers actually tell us information about its position in time. So typically in Postgres, the way that works is that numbers that are smaller than the current transaction ID indicate that that transaction happened in the past, and numbers greater indicate that that transaction happens in the future. And you might be wondering, why does it matter if we denote whether or not transactions have happened or not happened? And the reason is because transactions that are denoted as in the future should be invisible, actually, and they should not actually be visible to the transaction. So to clarify, you can imagine, let's say some transaction right here, T1 is sort of updating an account to have, we can refer to this as like the employee database again. So this transaction actually changes someone's salary to double that amount. And then there's some other transaction that, let's say this changes like maybe everyone's salary in the database to be double. And this other transaction, let's say it adds a new employee. So this, let's say like this has transaction number 99 and this has transaction number 100. So what this should actually mean is that to transaction 99, when transaction 99 is going on, transaction 100 hasn't happened yet. We don't change the salary of this new employee that's being added because this transaction hasn't actually happened yet. But it actually does make a difference because you could imagine, let's say this transaction ID was 98. That means that when we have 99 going on, then 98 has already happened. These are committed, and essentially these changes are all visible in the database. So that means this new employee that we added would actually get their salary doubled. So understanding when transactions happen is actually super important, especially as we start to think about concurrency and transactions that happen at the same time as one another. So actually having some system to denote txids is super, super critical. But what's really interesting about the way Postgres actually denotes and allocates these txids is that it's circular, which means that after you reach a certain point of txids or a certain number, they loop back around and we go back to the beginning. So you might be wondering, why do that? Why not just have them infinitely increase? But actually, this is a pretty smart way to do this. We have a set number of txids that can be allocated, and then we have a smart way of sort of reusing them so we don't have sort of an infinite number of just transactions that keep on running, and we can actually reuse these transaction IDs over and over and over again. But there is a problem that arises when we want to do this, because you can imagine, let's say we're sort of working our way around the circle, assigning more and more transaction IDs, but suddenly we get to a point where we're back here again, right? And now we want to assign a transaction ID of 101, but this transaction ID actually already has some information from the past. So this should technically appear as visible. You can imagine a transaction ID that is technically greater is supposed to mean that all of the commits from it, all the information in that transaction is invisible. But when you loop back around the circle, it might actually mean that this transaction that appears to be invisible is supposed to have some visible information to you. To clarify, let's go back to our example of what this means. So let's say that, this T2 transaction that we have up here added this employee, and we'll keep this as, to clarify, I'll remove some of this. We'll have this stay as transaction 100. We'll have this stay as transaction 100. And so that means initially we double everyone's salary, and then we add this new employee, and this employee does not have their salary doubled. They just have the normal salary. But then, we work our way around, and, this could be like millions of transactions later. Eventually, we're back at some transaction 99. And now, in this case, we're doing some other operation. Let's say like 99 is adding a new employee, and then let's say that transaction 100 is removing an employee. But essentially, this transaction 100 from the past added this new employee. We don't want this change to go away. We don't want this employee to appear as if they're not in the database to transaction 99. So you can imagine what we need to do is actually have some sort of history to say, hey, transaction 100, even though we're reusing this number, it has some sort of past. Transaction 100 in the past added this employee, it deleted this employee, it changed salaries by this much. So how do we denote that a certain transaction ID has already had some sort of changes and that we can't just ignore its history? This is where freezing comes into play. Now, this is something that's a really, really important concept in Postgres, where we essentially are able to mark a certain txid as frozen. Now, what that means to the vacuum that's sort of going through these database pages and getting information is that we shouldn't touch the information from this txid. So you can imagine we're looping around this circle over and over again, and then we come across 101, this txid right here, and we mark it as frozen. Now, what this frozen command tells the vacuum is we can think of the information and the history of this txid as permanently committed. We don't need to worry about this information because it's so old. So now, since we've marked this transaction ID as frozen, we know that all of the information that corresponds to its past and all of the information that was added or changed to the database from the transaction is committed in history. We're not going to change it. We're not worried about it. And most importantly, it's visible. So this current transaction that's going on, transaction 100, in this sort of future scenario where we want to remove an employee or add an employee, all of the information from the past is still visible. And to explain this in simple terms, you wouldn't want to be, firing an employee on a database in 2026 using information from 1999. This essentially ensures that the information that you're actually using to make your database changes is up to date, even though you're reusing these same transaction IDs. So once a transaction ID is actually frozen and we know that the information is committed, we can actually reuse that same transaction ID again. And this is sort of just marking it as available for use again. And this is sort of the beauty behind how Postgres has handled the txid wraparound problem with being able to freeze these transaction IDs and let the system know that the changes have already happened. So now that we understand txid wraparound, which is one of the major components of Vacuum, we have to dive into just one more aspect that's really important for understanding just how well thought out Vacuum is of a tool for database systems. And to do that, I want to cover two things. The visibility map, which is commonly denoted as the VM, as well as the free space map, or FSM. And I think these are almost kind of self-explanatory once you generally understand them. But to clarify, I'm using this sort of diagram here. And just to shout out the Suzuki database internals for Postgres textbook, a lot of the diagrams that I'm using in this video and other videos come straight from that textbook, and I recommend checking it out. if you want to get more in depth of an explanation. But essentially, the visibility map is what gives us quick information on whether or not the vacuum actually needs to scan individual tuples and clean things up. And you'll notice this recurring theme throughout just a lot of things in computer science and in Postgres specifically, which is how can we minimize costly actions that force disk accesses or like heap accesses, essentially like really costly operations, and how do we minimize that by making some sort of quicker solution? And so the visibility map essentially just gives us these sort of bits of information which tell us, hey, do I really need to spend time actually going through this page and identifying dead tuples or cleaning things up? And essentially, you'll notice that's what's happening here. So over here, we have the visibility map, and each of these bits right here corresponds to a different page header. And you can think of these as just full of information from the database. This page header will contain some row from our database here, and like we said, that could mean even like the employees database, and these sort of grayed out areas right here are dead tuples. And to clarify again, and to reiterate, these dead tuples just mean that it's not useful for our database anymore. So that could mean, for example, that maybe this tuple actually points to this now, and this is the most updated version, and this is some deleted old tuple that doesn't matter anymore. So what the visibility map tells us is, hey, instead of actually looking through every single one of these pages and every single tuple, just look at this bit right here. If it's a 0, then you know that you need to go in and vacuum things up, and you need to actually clean these dead tuples. If it's a 1, then that means there's actually no dead tuples to go in and clean up, or at least we don't want to look at this area right now. So in this example, what we know is that since there's a 1 for this first page, the vacuum actually just would completely skip this page header, and instead it could save its time and only vacuum the first and the third page, or 0th and 2nd page. So this is a really, really important concept, because this is how we make sure that the vacuum is actually a super speedy and efficient process. The free space map is kind of similar. It essentially just keeps track of the amount of free space that we have available. So you can imagine we talked a lot about how the full vacuum actually returns space to the operating system. And in this case, we know that the free space map is able to tell us some information about that, the amount of data and space we have available for data in our data pages. So you can imagine maybe there's some space here for being able to insert tuples and rows, and the free space map will essentially keep track of that. But the really important thing to note is, how do we actually update this information, and how do we get access to the VM and FSM? And so what actually happens is that when the vacuum is initiated as a process, we walk through a couple of steps. So the first thing we do is we scan each of our sort of pages to compile a list of the dead tuples, and we freeze old tuples. And we explained that earlier. This is exactly the core functionality of what vacuum is doing. The second thing that we do is we remove the index tuples that point to dead tuples. And we reallocate those sort of live tuples. And so what that means is, you can imagine there's sort of these indexes that are pointing to each of these tuples. There's one for each new row that we have created. And this index is what sort of denotes that we have information there that is valuable that we want to look at. So when we find these dead tuples, then we can immediately remove the index tuples that correspond to them. And then we can also this is marking the tuples available for reuse. And then after that, this is where we're able to take that information and we update the free space map and the visibility map. And this will be super, super important for when we want to actually have these sort of quick vacuum runs that run through and almost automatically in the background can sort of clean up these dead tuples that accumulate from a bunch of transactions that run up on the database. And then finally what we do is an actual index level cleanup. Now, I won't dive too much into the specifics of what actually happens here, but there's a lot more that happens from this vacuum process that you can understand if you know about things like the like the system catalog, as well as sort of removing unnecessary files and pages. And the index level cleanup actually is distinct from the earlier cleanup that we were talking about up here, because the step 2 that we're talking about right here, where we remove the index files, is actually locating the dead tuples and removing the indexes associated with it. Well, this step right here is reviewing the sort of overall structure and removing the excess indexes and the page bloat that exists throughout the entire database. So they are slightly different, but to go more into detail about this, I'd have to explain indexes a lot more in depth, where I'll save that for a future video. But in general, if you're curious about more about vacuum, I'll leave some links in the description if you want to learn more. And I really recommend checking out the Postgres Database Internals textbook by Suzuki. That's where a lot of the information in this video actually comes from as well.